Hello everyone, my name is Sergio, and today I'm going to be going through what the gradient descent method is, more specifically the stochastic version of this. And I find this is going to be really useful for future videos because I'm going to be using this to explain how learning works in neural networks. So yeah, I find this information kind of valuable in order to understand what's going on behind the scenes. But yeah, and gradient descent method is one of the easiest ways to implement learning, so why not go through it real quick. Okay, so one of the easiest ways to learn is by using the gradient of the error of a parameter j that j is to optimize. So yeah, we're gonna try to use the gradient of this error in order to update these parameters j and get a better, get our distribution closer to the true distribution. So in order to do this, we're gonna do jt plus 1. So this is gonna be equals to jt, our current value of j, minus epsilon, and then the gradient with respect to j of the KL divergence. Okay. This KL divergence is basically just going to measure the distance between the two distributions, where Qj is our distribution and P is going to be the true distribution. Here, epsilon is just going to be a small positive constant that it's just going to be a real number. Note small positive constant. Just gonna note it there, and note here that we have to have a value for jt even for the first step of the gradient descent, and therefore we're gonna have to find a way to determine j0 or j when t equals to 0. So we're gonna have to initialize these j parameters appropriately, and therefore for a change of delta j, which is just gonna be the small change between the updated j minus the previous jt. Then the change of the KL divergence is simply gonna be again a small change. Oops. Okay. And it's gonna be approximately equals to the small parameters in j, times the divergence with respect to j of, sorry, not divergence but gradient, sorry, of the divergence here this time, which is just gonna be equal, to minus epsilon, because again it's just a small positive constant that is gonna be as well delta j. It can be substituted by that, and then this will be multiplied by the absolute value of the gradient of the divergence again here. Okay, so from this we can see that the d, this would be our loss function in this case, is gonna decrease, right? And this is what we're ultimately looking for. We want to reduce the distance between our distributions for each step of in the updates of j. However, this process would require us to know the true distribution p, which, if we knew p, then we wouldn't need to estimate qj, and therefore it is something that is not really feasible in practice, right? So in order to be able to do something about this, we're gonna use a sampling approximation, and we're gonna derive therefore the stochastic gradient descent method, right? So for this, first we're gonna calculate the slope, yeah, the slope of the error. We can just substitute by the definition of DKL, sorry. It's gonna be the sum here over the parameters x and d, where x is just the vector, the input vector, and then it's gonna be the logarithm, the distribution over our distribution. All of these x's are vectors, keep forgetting about that. Okay, and this, we can just move the gradient into the sum. We're gonna end up getting the sum over x and d of the distribution times the gradient of the logarithm. I'm gonna try to fit this in here. Bit tight, but it's here. Let's put that into parentheses. Well, hopefully you understand what it says there. but yeah, from this we can see that the gradient of the error, like, it's the expectation value of this term here, and therefore we can consider approximating the expectation value, this expectation value, with simply by sampling an average from the distribution P, right? So this can be indicated with the following notation. We're gonna want to sample a set of points xi and di from the distribution P again, for I, as many data points we want to sample until n, and therefore we're gonna create an approximator out of this, as the sample average approximator. So we're just gonna call it G, and this is gonna be the sum from I equal to 1 to however many data points there are as well. We're just gonna add this term to remove bias, and then this is just gonna be the gradient of the logarithm, this time in terms of the parameters that have been sampled for each of the i's. There's gonna be an I here, and then it's gonna be the same, but for our distribution. Okay, and therefore this is gonna be our estimator, and due to the law of large numbers, for a large n, then this should be a good approximator for the average of P. And yeah, we call this stochastic gradient method, and more specifically the algorithm uses this methodology in the following steps to optimize, right? So let's do stochastic gradient descent, sorry. So it has a couple of steps, right? The first step is gonna be j equals to 0, right? To set this up, initialize the parameter. It has to be done properly, because a poor choice of j when t equals to 0, it could lead to a really bad approximation or divergence even. And then we're gonna do a loop of the following steps. First, we're gonna sample n data points, and then we're gonna calculate with these data points, we're gonna calculate or compute the approximator G, sorry, this one, the one we just did above, and we're gonna use this to update our parameters J. And we would just subtract this times the epsilon. All right, fair enough. This is how ideally a stochastic gradient descent method would look like. However, there are some variations of this that are more suitable for practical applications. For example, when the data is limited, we would have to change this a little bit and do mini-batch learning, or is known as mini-batch learning. And it's something really similar, actually. Let's just display this here. So mini-batch learning. which is just gonna be okay. So here we would have a set of data points, right? Again, that is just gonna be given to us, and this is just for I1 to whatever until n, and then again one initialize j, the first j, t equals to 0, yeah, and then we're just gonna do another loop. Well, the first one in this case, we're gonna first divide the data into let's say m mini batches or batches, whatever, at random, no 2 points, sorry, okay, at random, and then do another loop inside this, and we would just, you know, replace the data that of each of the mini batches, and then plug it into g, sorry, for each of the m batches. That's why we're looping, right? Because we want to do the same for each of the batches, and then just update our t value. Well, we can just do it again, yeah. It's gonna come from j t minus the epsilon j again. Okay, so in deep learning we're gonna use something similar to this. However, how we call the KL divergence, it's gonna be, instead of this KL divergence, it can be an error, any error function really, and because we have to compute gradients and therefore we have to do a lot of differential calculations, we're gonna be using, or neural networks usually use an algorithm that is called backpropagation. But yeah, hopefully I managed to explain myself clearly, and now you understand, or at least have a notion of how the gradient descent method and the stochastic version of this work. But yeah, thanks for watching. If you got to this point, I appreciate it, and I would also appreciate some feedback in the comments or whatever opinions you have. I'm all ears. Yeah, see you in the next video.